believe I forgot that. Kat, thank you so much for the student who just reminded me to record. Wow. So what is the nature of spiral nebula? Let's return to Isaac. Sorry. So Pierre Laplace theorized that the solar system emerged from the collapsing glass, from that phrase that you see up on your screen. And as it collapsed, it rotated faster and flattened. Why did it flatten? Oh, I'm so thankful for student for reminding me. If you could all remind me every lecture to record, I haven't forgotten yet this semester, but I mean, I've forgotten several times, but at least I've recorded most of it. So why does it collapse? We've shown this video before, but I think now is the time to show it again.
Our Sun and the Earth, and all the planets and moons and dwarf planets and asteroids and comets, the solar system in short, formed about 4.6 billion years ago from a nebulous cloud of swirling gas and dust, which coalesced thanks to the irresistibly attractive force of gravity. However, this nebula started off more or less as a big shapeless blob. So how did our solar system end up with all the planets and their moons orbiting in a flat disk? I mean, we've all seen the planetary model of the atom, which is definitely wrong when applied to atoms, but it also kind of suggests that planets might revolve around the sun every which way. So is our solar system somehow special in its flatness? Or is the planetary model of the atom doubly wrong? Well, our solar system definitely isn't alone. Many exoplanet star systems are flat, a lot of galaxies are flat, black hole accretion disks are flat, Saturn's rings are flat, etc. So why, when there's all of 3D space to fill, does the universe have this preference for flatness? The answer has to do with two things: collisions and the fact that we live in 3 dimensions. Bear with me. Anytime a bunch of objects held together by gravity are zooming and circling around, their individual paths are nearly impossible to predict, and yet collected together they have a single total amount that they spin about their center of mass. It may be hard to figure out exactly what direction that rotation is in, but the mathematics implies there must be some plane in which the cloud, taken as a whole, spins. Now, in 2 dimensions, a cloud of particles rotating in a plane is flat by definition. It's in 2 dimensions. But in 3 dimensions, even though the rotation of the cloud is given by one plane, particles can whiz around far up and down from that plane. As the particles bump into each other, all of the up and down motion tends to cancel out, its energy lost in crashing and clumping. Yet the whole mass must continue spinning inexorably, because in our universe, the total amount of spinning in any isolated system always stays the same. So over time, through collisions and crashes, the cloud loses its loft and flattens into a spinning, roughly 2-dimensional disk shape, like a solar system or spiral galaxy.
Okay, so that's a reminder that through these collisions, any gas cloud will have a certain amount of angular momentum, and as the cloud collapses through collisions, it will conserve that angular momentum, and we have a flat disk. Okay, and that's true for solar systems, but it's also true for galaxies, as we'll find out. So let's go back to this debate about what's the nature of these spiral nebula that seem to be everywhere, no matter where we looked with our powerful telescopes. And this takes us up to 1920, where there were 2 people who were suggesting different things. Harlow Shapley suggested that these are just early solar systems, which made a lot of sense because we knew that solar systems had to be created through collapsing gas clouds, and as they collapsed, they would form these flat spiral disks. And so many people assume that would be a very natural. Instead of 2 things, we have 1 thing, which is forming solar systems. There was a problem with that, though. Well, let's get to the other person on the side. Edwin Hubble suggested, no. These are not solar systems. These must be very, very far away. And what we're seeing is not gas. What we're seeing are actual stars, but they're so far away that all the stars bundled together look like a bunch of gas. Okay. And the debate points is that these spiral nebula had very high redshifts. And these very high redshifts, remember, this was early in the understanding of Doppler shift of spectral signatures. And so a lot of people thought, well, gee, there must be another cause for these red shifts other than the fact that they're moving away from us very quickly. And also there were novas. We saw stars that we saw parts of these spiral nebula that seemed to brighten. And if those were nebula, then they had to be very far away. But again, people thought, well, gee, maybe it's something else that's brightening. So this is for 5 years people debated, and I think most people bet on Harold Shapley, because what Edwin Hubble was suggesting was something that was literally inconceivable. The fact that the observable universe was vastly, vastly larger even than the vast universe that they had suggested. And it was consistent with the current theory of the formation of the solar system. Well, so that brings us to January 1st, 1925. Y'all remember that date. And Edwin Hubble had a very, very high resolution picture of the Andromeda Galaxy, which is one of the closest galaxies to us. And he discovered one point in that image that was what we call a Cepheid variable. And we'll be talking about Cepheid variables in just a few minutes. And Cepheid variables oscillate, and the speed of that oscillation tells you how bright it is. And so by looking at how bright the Cepheid was and how fast it oscillated, he was able to calculate the distance to it. That distance was several million light years, which means this could not be in the Milky Way galaxy. It had to be external. And that was conclusive proof of his island universe theory. So we no longer call them spiral nebula. We now call them spiral galaxies. So that was the discovery of galaxies. Ever since then, we've known that the universe is vastly larger than we can imagine, and that the Milky Way galaxy, the galaxy we live in, is just one of trillions of other galaxies. So what do these galaxies look like? Well, we've mentioned that there's spiral galaxies, but there's other shapes too. Even spiral galaxies have different weird shapes. And then we have the Small Magellanic Cloud is what's known as irregular. This is what's known as an elliptical galaxy. And then we have spiral galaxies. And spiral galaxies will look different depending on their orientation to us. Okay. So here, galaxies, for the purposes of this course, I really divide galaxies into three categories. There's elliptical galaxies, which they don't really have any visible spiral arms. They tend to be red, and they tend to have almost no gas and dust. This will be important later as we talk about that. Spiral galaxies are by far the most common galaxies, and they're disc-shaped, as we've talked about. They contain lots of gas and dust. And they have various different subcategories that you're not going to be responsible for, such as barred spirals and SBs and all sorts of weird stuff. And they tend to be very blue. Irregulars are, as they say, they're very irregularly shaped. They're not spirals. They're not ellipticals. They tend to be smaller, but they also have a lot of gas and dust. So ellipticals have no gas and dust, and they're red. Spirals have a lot of gas and dust, and they mostly are blue. And then irregulars have a lot of gas and dust, and they're just various colors. So now here is the what's known as the tuning fork diagram of the different subcategories. You are not responsible for these subcategories. One problem with this diagram, which has been around for 100 years, is that this implies that there is an evolutionary path. There is not. Okay, it's not that ellipticals then turn into spirals. This graph is just a way of categorizing them. And I don't memorize this graph. What you need to know is there's ellipticals, there's spirals, and there's irregulars. Okay, so ellipticals range from huge giants to really small ones. They have no disk, no arms, no gas and dust. The spiral galaxies we talked about, and then irregular galaxies. Here's a video of what's known as the Hubble Ultra Deep Field Image. Back a few years ago, Hubble was ordered to look at one part of the sky that looked blank and stare at it for several hundred hours. And here's what Hubble saw. So every single dot you see is a galaxy, every single one. Those are all galaxies. And you might notice that most of these galaxies are really, really red. They're not red because they're red. They're red because they've been so red shifted. They're moving so fast away from us that they now look red. And so when I say that ellipticals look red, I mean if we didn't have the redshift to worry about. But here, almost all these galaxies are reddish, and that's again because of the extreme redshift. Every point is a galaxy. It's the most famous astronomical image ever. Anyway, so here is kind of a breakdown of the galaxies. The bottom of this graph is a breakdown of the galaxies when we look very far away from us. And very far away from us, the majority of the galaxies were irregular. And then we have spirals, and then we had elliptical galaxies down here. If we look at galaxies that are close to us, which means near the current time, because this is hard to conceptualize, the farther away we look, the farther back we're looking, not only in space, but also in time. So as we look at the farthest galaxies, we're looking to the early days of the universe. If we look close by, the vast majority of the vast majority of galaxies are spiral galaxies. And then we have some ellipticals and some irregular. This graph, it says peculiar, but that's just it. So let me show you just some videos. How is the whole area filled with galaxies rather than our own stars? Is it just an empty region of our sky in our own galaxy? Yeah, so that's a good question, Art. In fact, let me bring up the Milky Way galaxy for a second. Hold on. Okay, so let's kill all these things. Remove all object labels. Huh. Oh, here we go. Okay, so we're embedded in the Milky Way galaxy. What Hubble did was they wanted to see, they wanted to look at the farthest reaches of the universe. And so what they did is they focused the camera not anywhere near this plane, but directly, I don't know if it was up or down. So they tried to avoid most of the Milky Way galaxy. And so those pictures were, taken up. And so they just took a random part of the sky that looked fairly boring. And that's what they saw. This kind of blew people away. There was really no expectation that they would see this many galaxies. We can show here galaxies, show all galaxies. Okay, so here, marked by points, these are the galaxies that are just close by to us, okay? And let me show you another video of that. So, new share, starting at less. Okay, so here is planetary program. Let's go to deep space, local group. So here's the Milky Way galaxy. And there's the Andromeda galaxy. And one thing to notice is that the Andromeda galaxy and the Milky Way galaxy are relatively close to each other, okay? In other words, they're separated by about a million light years, and they're both about 100,000 light years across. So they're separated by a factor of 10 to 1. Whereas stars are separated by a factor of 100 million to 1, not 10 to 1. So stars, relatively speaking, are very, very far away. And Milky Way galaxies are relatively close. And that has ramifications for In fact, you can see it here, how close these are. Okay. In fact, we have two galaxies, the large and small Magellanic Clouds, that are almost on top of the Milky Way galaxy. So this implies that galaxies collide all the time, which they do. Okay. And in a future lecture, we'll talk about those collisions. And so here's the nearest galaxies to us. You see, space is just riddled with galaxies. It's lousy with galaxies, as they say. Okay, let's kill this. Share. And go back to lecture. Okay. So here, a galaxy that appears to be populated by mostly red stars is likely A, has never had blue stars in the galaxy. B, has had blue stars that were not present anymore, but were at one long ago. C, has been around long enough for blue stars to evolve into red main sequence stars we do see. D, never contained enough gas to have blue stars develop. E, had blue stars that are being blocked by dust. So let's bring up the polling. Okay. So click in what you think. So Hannah, yes, the slides will be posted for this lecture. I post all slides. I usually post it beforehand. I'm sorry, I forgot. I'll post it immediately after lecture. Okay, so there is not a good consensus here. I was hoping you think about this. So can you put me in text of why would ellipticals be red and spiral galaxies be blue? Huh? So put your answer in the chat, please. Why are ellipticals red and spiral galaxies blue? Yeah, that's correct. Ellipticals, and Sam has it exactly right. So the spiral galaxies have gas and dust. If you have gas and dust, you can form new stars. And some of those new stars are going to be OB stars, those really, really bright blue stars that don't last very long. Whereas elliptical galaxies, if they don't have any gas and dust, they can't form new stars. So there's no way to form new stars. There's no way to form blue stars. And so remember, blue stars only last a few million years. So they would have been long gone. All that's left in the elliptical galaxies are the old red stars. Because remember, in the HR diagram, the bright blue stars in the left of the diagram, they don't last very long. The red stars in the right, lower right of the diagram, they last forever. So that's exactly right. And so answer B is the correct answer here. So that tells us something about ellipticals and spiral galaxies. And we'll get into that in a future lecture when we talk about galactic collisions. But ellipticals typically don't have any star formation because they just don't have any gas or dust to create those stars. And blue is a marker for star formation. When you see blue, you know stars must be forming right now because blue stars don't last very long. Okay, so now we're going to switch subjects and talk about the distance ladder. How do we calculate the distance to other galaxies? Distance is really important. So this map is from the 1500s, when they were trying to, late 1500s, when they were trying to map North and South America. And one thing to notice on this graph is that they were able to get the latitude very accurately, how high or low you are from the equator. They couldn't get longitude. And there's technical reasons for that because they didn't have clocks that could measure that. And so here, to actually know the shape of North and South America, it's really important to be able to know longitude. And this took hundreds of years to figure out how to map this appropriately. And we can overlay this with a current map. And you can see latitude's pretty accurate. Longitude is just badly, badly inaccurate. There's a great book called Longitude talking about the search for the method to find longitude, by the way. So in terrestrial case, distances, in this case, longitude, was critically important. The same is true for distance in astronomy, okay? One way we measure distance is by looking at the difference between intrinsic and extrinsic brightness, how bright something appears and how bright they really are. So here are candles, and a candle, the flux, the brightness of an object drops off as 1 over the distance squared. So as I move from a distance of and so if I want 1/4 the flux, how many times distant would that be? Anybody? That's correct. 2. Thank you, Bree. So, so as I go from 1 light year to 2 light years, the intensity of light drops down by a factor of 4. So knowing that, if you know how bright something really is and you know how bright it appears, you can calculate the distance. Or if you know the distance and you know how bright it appears, then you can calculate how bright it really is. Okay. So the brightness equals the intrinsic luminosity over the distance squared.
Okay, one last time. These are small, but the ones out there are far away. Small, far away. Forget it.
So same thing. When you see something, you see a bright star, you don't know if it's bright because it's close or it's bright because it's intrinsically bright. But there's ways to figure that out, as we'll talk about shortly. So if you can just put in the chat how you think we can find the distances to these stars or the distances to galaxies. So what are the ways that we can calculate this? We've already talked about a little bit of that, but just give me some ideas here. Find stuff for predictable brightness. Sam, that's exactly right. And remember, if 90% of the stars are on the main sequence tells us what their intrinsic luminosity is. And so if we know that they're a main sequence star, and we know how bright they appear, we can calculate the distance. Anything else? We've mentioned a few of these during the lectures, so you should be able to think about it. That's right. It's actually called Cepheid variables, Laurel, but that's correct. There's a type of star that oscillates with a certain frequency, and that frequency increases the brighter it really is. And so if you can measure the frequency, which is really easy, then you know how bright it really is, and you look at how bright it appears, and that will give us the distance. Anything else? And we actually talked about this technique in earlier lectures. I really miss lecturing in person where I could actually just go up to one of you and say, hey, what do you think? Yeah, so Laurel, again, that's exactly right. We do have something about supernova. We'll be talking about that. And globular clusters is another mechanism. But another mechanism we have talked about in previous lectures called parallax. Sorry, not parallel, parallax. Anyway, let's go over these in detail. So here's what we call the distance ladder, the different ways that we look at that. There's actually additional mechanisms, but these are just the ones that you're going to be responsible for in this course. There's about 3 or 4 others that I don't mention. So one is just physical measuring. Just we can just measure the distances to different planetary bodies, planetary bodies in the solar system, just by frankly measuring it, just by shooting a laser at it or shooting a radar beam at it. We can also do it through Kepler's laws. We'll talk about that in a minute. Parallax. This is something we mentioned in an earlier lecture. That works for nearby stars Distant stars, this is something that, as Sam mentioned, main sequence fitting, since we know the intrinsic brightness of main sequence stars. Then there's the Cepheid variables, which Laurel mentioned, and we mentioned earlier when we talked about spiral nebula. And then the farthest one is what we call type 1A supernova. So I don't, in your textbook, you're going to see type 1A, type 1B. That's just too much detail for this course. So I use type 1 to really refer to what the textbook calls type 1A, which is the carbon explosion, carbon implosion, the one where the white dwarf shrinks and all the carbon explodes all at once. Okay, and then we'll talk about the cosmological redshift in a minute. So here's Kepler's law. If you know how fast an object is moving in its orbit, we can calculate the period squared equals the submajor axis cubed. So if I know the period of the orbit, it can tell me the size of the orbit, and that will tell us the distance that the planets are. And we can also measure those distances of very far objects. So if we see an exoplanet circling a star with a certain period, that will tell us the size of that planet's orbit around that star. And it will also tell us how close it gets to that star, which tells us whether it's in the habitable zone, which we'll be getting into in a future lecture. Nearby stars, parallax. This is something we talked about. You go to different size parts of something, and it will tell you how far away something is. Parallax is where the planet, the Earth, will go from one side of its orbit to another. And as it goes from one side of the orbit to the other, a nearby star will shift its position relative to the background stars. And that shift will tell us how far away or close it is. So those stars there that aren't moving are very far away. This star, which is moving against the background, is actually very close. Okay. So let me show you a that. Let's go to here. New share. Okay. And let's explore. There we go. Okay. So here we've got there's a sailboat, and we want to measure the distance to it. We can take a measurement here, and then notice as we move on the road, the position of the sailboat relative to the back of the lake changes. And so with those two measurements, with the angle that this sailboat is from this part and from the sailboat is from this part, using just basic trigonometry, I know how far I moved on the road. And if I know those two angles, the distance in those two angles will give me this distance here. And that tells me where the sailboat is. Now, let's say that I take a measurement here at an unknown location, and then I take a measurement here. And note these two measurements, there's an uncertainty in these angles. And so these uncertainty in the angles that I'm taking the measurement of will produce an uncertainty in the distance of that amount. Okay. So let's take this measurement here. And here, in this case, I can't move very far in the road. And so because I can't move very far in the road, the uncertainty in my distance measurement is now huge. And so this is why when you have a star that's relatively close, and so the distance as the Earth moves from one side of the orbit to the other is large relative to that distance, then we have a low uncertainty. But if the distance that the Earth can travel in its orbit from one side of the orbit to the other is really small relative to the distance, then the uncertainty in the position of that star is huge and it becomes worthless. So this is why parallax only really works for close stars. And you recall from a previous lecture that We use, I tend to use light year to represent distances, but there's another distance that is used throughout the book and used throughout astronomy, and that's called parsecs. And a parsec is the distance at which the parallax is 1 arc second. And remember, in terms of angles, the sun and the moon are 30 arc minutes. An arc second is 1/60th of an arc minute. Our eye can see about 1 arc minute resolution. A good telescope can see about 1 arc second resolution. Okay, so 1 parsec is equal to a 3.26 light years. And so a star that is 1 parsec away, which is 3.26 light years away, would shift across the background by 1 arc second, which is just about what I could perceive with my little 4-inch telescope. So you observe 2 stars over the course of a year and find that both stars have measurable parallax angles. Star X has a parallax angle of 1 arc second. Star Y has a parallax angle of 0.5 arc second. Which star is closer? Yeah, forget D and E. Sorry. Okay. So a little bit more than half of you chose one versus the other. So let's go back a few slides. You see these background stars are not moving much. This star is moving a lot. Which of these stars is closer? Okay. So think about this. If the star is close, what does that angle look like? If the star is far away, what does that circle look like? So let's try this again. Same question, try it again. Huh. This is exactly wrong. Huh. Thank you. Let me make note of that. So in fact, the star Y, star X is closer because it has a larger parallax angle. And you can that's just common sense. If you blink your eyes back and forth, if something shifts, it's very close to you. If it doesn't shift, it's very far away from you. Okay. I don't know how I missed that. Anyway, so that is parallax, which gets us nearby stars. Farther stars is the main sequence fitting, which is what I think Sam mentioned. So if we have different types of a bunch of stars, we can fit it to the main sequence and calculate the distance. And so let's go try that. Okay. So here is, this looks confusing, and I apologize for that, and it is a little confusing, but this is real important. So here we've got small m, which is the magnitude of a star, and big M, which is the absolute magnitude of the star. So here, if small m equals big M, then the distance is 1 parsec, okay? Because remember, the distance, the magnitude, the absolute magnitude is equal to the apparent magnitude and distance. I thought of 10 parsecs, but in any case, here as we go from, oh, there it is. Okay, it is 10 parsecs. So remember, magnitude is how bright things appear. So magnitude, remember, magnitude 1 star is very bright, a magnitude 6 star is very dim. We introduced the concept of absolute magnitude a while ago. Absolute magnitude is the magnitude that the star would appear at 10 parsecs. And so here we have magnitude 5 and absolute magnitude 5. The distance is 10 parsecs. So this all matches. Okay, that all makes sense. So let's say that that magnitude 5, absolute magnitude 5 star is actually at a distance of 100 parsecs. Okay. Well, okay, that's close enough. So here, the big M, its intrinsic luminosity has stayed the same. It hasn't changed. Okay. But because it went from 10 parsecs to 100 parsecs, its small m magnitude is 10. And 10 is, I couldn't observe it with my telescope. The eye can really only go down to magnitude 6. So we went from a relatively bright star in the night sky to a star that is just not visible in a small telescope. Okay. But if I'm able to if I'm able to observe it and say, oh, that's a magnitude 10 star, and through outside information, I know its intrinsic brightness is 5, this equation will give us the distance. And again, so yeah, Sam, I thought it was 10 parsec too, but when I redid it did pop into it. That was just a mistake in the program. And so note that here, if I know I observe a magnitude 10 and I know it's intrinsically magnitude 5, this equation will give us the distance, which is about 100 parsecs. You're not going to be responsible for this equation, but what you are responsible for is if I know the apparent magnitude, how bright something appears, and its intrinsic magnitude, in other words, how bright it really is, I can use this equation to calculate the distance. So let's lock the distance here. So now we have stars at a distance of 100 parsecs. And let's say that it is magnitude 5. In other words, it is a magnitude 5 star. What that means is its intrinsic brightness is magnitude 0, which is really, really bright. Okay. So if outside information tells me that its distance is 100 parsecs, then I can tell you based on how bright it appears what its intrinsic luminosity is. So intrinsic luminosity will give us distance. Distance will give us intrinsic luminosity. Is there an easy way to tell if a star is main sequence? Yes, there is. So Sam asked, how do we tell if a star is main sequence? We do it through things we haven't talked about in this course, which is the spectra of the star. Stars that are not on the main sequence will have very different spectra, and there's ways to separate whether a star is main sequence or not. Actually, I'll be able to show you that in a future simulation. Okay, so this is using this equation to calculate distances based on the difference between the intrinsic magnitude and the magnitude as it appears in the night sky. So let's go to here. So here is the main sequence, okay? And there is a main sequence star, and this star has an apparent magnitude of 1, and if it has an apparent magnitude of 1 and an absolute magnitude here of 0.48 based on where it is in the HR diagram, that gives us a distance of 1.7 parsecs. So as we go up on the main sequence, notice what happens. As we go up on the main sequence, the intrinsic brightness here goes up. Well, it becomes a negative number because that is just the luminosity expressed in magnitude numbers. So notice that number changes, and as we go up, the distance changes here. Okay. So let's get a more reasonable apparent magnitude, say 5. Okay, so 5 is a star that we can see in the night sky. And so a G-class star, if it's 5 on the night sky, it would have to be 9 parsecs away, which is very close. As we go, if that is an O-type star, it's 1440 parsecs away, which is very far away. Okay. So because the main sequence here tells us the absolute luminosity, which tells us the intrinsic magnitude, the big M, and the little m, how bright it appears, using this equation, it will tell us the distance. Okay. So as we go down and then up. And so Sam asked if we can tell different types of stars. Those different types of stars were told by spectra, which are responsible for us in this course. And those are different luminosity classes. And those, as we choose different luminosity classes, we go on these different lines here. But in this course, we only talk about this luminosity class, which is the main sequence. Okay. So this what they call spectral parallax is a very, very powerful way of calculating distances. If you know a star is a main sequence and you know its color, then you know what its absolute luminosity is, and you also know what its intrinsic magnitude is. And if you know how bright it appears on the night sky, using this equation, it will give you the distance. Okay. Let's go back to this. So, and now, so that's main sequence fitting for that. What happens if we see a cluster of stars, such as a globular cluster? Then we can go do something even more fun. So here is the main sequence. And let's select a cluster. Let's do a better cluster. Here's a cluster here. And this clearly is the main sequence right there. So we bring it up to the main sequence. We say the apparent luminosity of that main sequence is 9.4. The absolute luminosity is 3.5. And that cluster is 151 parsecs away. So Sam, instead of looking at the spectra of each of the stars, we can just look at where the stars are clustered, just as you suggested. Okay. Let's choose a different cluster. And so here is a globular cluster. And so we have 3.5 there. Let's do 12.5 there. And that's 631 parsecs away. And notice also we've got this cutoff here, which we talked about previously. And the Pleiades, bring it down so it matches. This is 9.1. And the Pleiades is 132 parsecs away. Okay, yeah, that's just so cute. Yeah, let's skip over this. Before we talked about the fact that these clusters, you can look at the turnoff point of the cluster, and that tells you how old the cluster is. Okay, as you saw in one of these graphs there. So, and then we talked about the Cepheid variables, which the oscillation period is tightly correlated with the intrinsic luminosity of this. And notice they're very, very bright, 30,000 times the brightness of our sun. So because Cepheids are so bright, we measure the oscillation period. That tells us what the intrinsic brightness is. We know how bright it appears in the night sky. That will tell us the distance. And so as we get farther away, even to the closest galaxies, we can use Cepheids to really tell us those distances. So we start off with, Kepler's laws. We go to parallax. We go to the Hertzsprung-Russell fitting, what we call spectroscopic parallax. Now we're talking about Cepheid variables. Okay, but that only goes out to 25 megaparsecs away, about 75 million light years. And our galaxy is, I think it's 50 billion light years across. So it doesn't go very far away, relatively speaking. So for the most distant galaxies, we have to go with what we call type 1a supernova in the cosmological redshift. If you remember the two types of supernova we talked about, one is the core collapse supernova, and the other one is the carbon explosion supernova, carbon detonation supernova. The carbon detonation supernova happens when the white dwarf accretes enough material that it hits the Chandrasekhar limit, which is 1.4 times the solar mass. And when it hits that limit, the white dwarf collapses and the entire white dwarf explodes all at once. What this means is that all type 1 supernovas explode in exactly the same way because they're exactly the same mass and they all explode everything all at once. And so we would expect that type 1a supernova would all have the same intrinsic brightness, which means if we can see how bright they appear, then we know how far away things are. And the nice thing about type 1a supernova is that they are the brightest things in the entire freaking universe. And so we can observe these supernova explosions all the way to the very edges of the observable universe. Okay. So all we have to do is to fit those curves to the supernova explosion. And so let's show you that. So let's say that we observe a supernova. That's not a very good one. Let's try another one. There we go. We observe this supernova. Let's try a better one. Here we go. And we move it in both time and space. And so there it matches up with what is the stereotypical light curve. The supernova will get really bright, it will drop off, and then it will have this tail. And so we take the data points of this observation, we move it in both time and space until we get there. And so now we have 17.4 as the apparent magnitude. The absolute magnitude based on computer models, minus 16 there, gives us a distance of 47 megaparsecs, about 180 million light years, okay, just by moving those over. And so let's try another one. Okay, that's about the same. Here's one, 18.3. This one is 72 million parsecs away. Move this one down so it matches exactly. 15.8. And that's 22 million parsecs. So you can see that this shape, matching these type 1 supernova are very, very powerful for going for the farthest distances. So here are the 5 rungs of the distance ladder that we talk about in this course. Kepler's laws, so parallax, main sequence fitting, also known as spectral fitting, spectral parallax, Cepheid variables, and then type 1a supernova. Okay. And we talk about sources where we know the intrinsic luminosity as standard candles. So when you see the term standard candle, that refers to things like Cepheids or type 1a supernova, where we know how bright they really are. Okay. So that's it for the distance ladder for now. Now we'll talk about Hubble expansion. And again, going back, oh, shoot, I'm sorry. I'm not showing you the right thing. So I was talking about this and you weren't seeing it. So here are the distance ladders so far: the solar system, parallax, main sequence fitting, Cepheid variables, and type 1a supernova and cosmological redshift. And we use the term standard candles to refer to things where we know the intrinsic brightness of them. And so if we know the intrinsic brightness of something, then we can, if we know how bright it appears, we can tell how far away things are. So that's it for the distance ladder for now. And now we'll talk about Hubble expansion. Same guy, Edward Hubble, noticed that the dimmer galaxies were, the more red shifted their spectral lines were, shifted towards the red. And they knew at the time that red shifted meant things were moving away from us. And it seemed kind of weird that virtually all galaxies where he measured the redshift of were moving away from us. And the dimmer they were, the faster they were moving away from us. And this created what we now call is Hubble's law. And Hubble's law says that there is a relationship between the distance of galaxies. Now, he was talking about just how bright they are, but he was saying, well, dimmer galaxies must be farther away. And so, his observation was how bright they were relative to how fast they were moving away from us. He then interpolated that saying, well, assuming that galaxies are all approximately the same brightness, then if they're dimmer, they must be far away. Now, that assumption wasn't true, but it was true enough for him to be able to create this graph, which is giving a relationship between distance and velocity. So the farther away galaxies were, the faster they were moving away from us. And that's codified in what's known as Hubble's law. The velocity of recession is equal to this Hubble constant, h naught, times the distance that the galaxy is away from us. And this is one of the most important mathematical laws in all of cosmology. What that says is, as the universe expands, more distant objects recede from us more quickly. This is known as the cosmological redshift, as opposed to the day-to-day redshift, which is just a measure of the velocity. And here it's not a measure so much as the velocity as the expansion of the universe. And what do I mean by that? Well, unfortunately, I'm going to have to show you using the analogy that virtually every astronomy professor since the beginning of time has used, and that's blowing up a balloon. Okay, so here is a balloon, and the balloon has a bunch of coins on it. Those coins, you can imagine those coins are galaxies. And as I inflate the balloon, the coins that are relatively close from me are going to be moving away from me at a relatively slow speed. The coins that are far away from me are going to be accelerating at a fairly rapid pace. So let's decrease the balloon and now increase it again. So again, coins that are far away from me are going to be moving very rapidly away from me. Coins that are close are going to be moving away from me relatively slowly. And here's the thing. Every coin on this balloon would see exactly the same thing. Okay? Every coin would see exactly the same thing. And so there is no center of this expansion, although it does appear that all of the coins are moving away from us. Okay? And this is known as recession, the Hubble constant h naught. H naught is now measured as 70 kilometers per second per megaparsec. Okay, let me show this video and then we'll open that up for questions.
The universe is expanding, so does that mean there's a center from which everything is stretching outwards? I mean, it looks like the center is here because this point didn't move when we scaled, but we could just as easily have watched the scaling from this star, or this one, and they each look like the center. In fact, anytime you scale anything up or down, there's no real center to the scaling. I mean, this square was clearly scaled up from its center. I mean, its corner. I mean, that point over there. The point is, sure, there may be points that stay in the same place because of your frame of reference, which is why it appears to us as if the Earth is the center of the expansion of the universe. But to someone in the Andromeda Galaxy, it would appear that they were the center of the expansion. In short, if you're too close-minded to view the universe from different perspectives, it's easy to think you're at the center of the universe. Maybe that's the universe's way of making us all feel special. But really, we're not.
Okay, I'll finish
This
up
episode of
I'll finish up that lecture next week. I'm sorry, on Thursday, and I'm open for questions. Thanks so much. Any questions? So why is the universe expanding? Anybody? Do you know the estimated edge of the universe? So, Allison, yeah, that's a good question. You will often hear me use the phrase observable universe, and I use that phrase because the universe is expanding, and that expansion rate increases as we get farther away from us. And at some point, that expansion rate will exceed the speed of light. And once we hit that point, we cannot observe anything past that point. And so that's what we call the edge of the observable universe, because we literally cannot observe anything past that point. The universe is about 13.8 billion years old. The edge of the observable universe, from our perspective, is, I think, about 49 billion light years, somewhere in that range. So we cannot observe other galaxies that are farther away than that. The universe could be vastly larger than we know, but we will never know because we can only observe out to the, well, not to be redundant, the edge of the observable universe. Could we theoretically determine the center of the expansion if we collected multiple measurements from different points? Or would they all just give the same measurements relative to ourselves? So, Hope, think about the balloon is a perfect analogy, except that it's two-dimensional versus three-dimensional. Where is the center of the expansion of the balloon? It's nowhere on the surface of the balloon. If there is a center of the expansion of the balloon, it's outside the surface of the balloon. So if you think of our universe as a three-dimensional object, there's no center of the expansion. It expands everywhere in every place. Another analogy that people use is a raisin cake. As the raisin cake expands, different raisins within the raisin cake, as it's cooking and expanding, recede from each other, but there's no center of that recession. So, in fact, there is no center of the universe. That's just it. Does the universe expand faster with time? What determines the expansion rate? So, Gracie, one of the greatest discoveries, if not the greatest discovery of the 20th century, happened in 1998, 1999. And that involved the expansion of the universe. And it just, we have an observation that has no theory behind it, and it will blow you away. And we'll be talking about that in a future lecture. The fact that so much in astronomy is happening so recently to our times, the fact that we have something that happened in 1998 that completely revolutionized our opinion of what the future of the universe is, the fact that, we have 10 times more dark matter than normal matter, and we don't know what dark matter is, the fact that we observed gravity waves colliding neutron stars and images of black holes for the first time just in the last few years, it's just an amazing and dynamic field. And hopefully all astronomers and cosmologists believe that there does exist a objective reality independent of us and independent of politics. It doesn't matter whether you're Democrat or Republican, a supernova explosion is going to be the same. That we believe in objective facts. Most of us do. Other questions? So as this course proceeds, we're going to get more and more cosmic, literally. We'll be talking more about what it all means, why the universe is, where the universe is going, what the universe, the fact that the universe had a beginning, and the fact that the universe has an end. Okay, which is a little frightening. Other questions? Feel free to turn on your mic if you want to ask a question audibly. Could it be said that the universe is expanding from the side of the Big Bang? Sam, that's what a lot of people say, but that's just absolutely not true. The universe was the Big Bang. The entire universe was the Big Bang. And so everything that exists now existed at the Big Bang then. Okay. And the Big Bang existed independent of time and space because the Big Bang created our time and space. And so there is no point inside the universe that the Big Bang occurred. The Big Bang occurred of the universe. The Big Bang was the entire universe. It permeates all of time and all of space, just like the Force. Any other questions? Okay. Thank you so much. And I'll see you all on Thursday.